professor at the University of North, and also part of the UNISA Africa Chair in Nanoscience and Nanotechnology. He was vice supervisor. Let's see, like does continue like that. And today he will be giving us a talk titled X-rays nanoscopy of calcium carbonate, the key materials in the daily life. But to show you that behind this presentation, the idea is that Prof. and Najibou will continue and sustain this cooperation between us involving three institutions that will be University of Oman, University of South Africa, and as well as Itamba Labs. We will see that within this presentation, what the number of advanced techniques are used, in particular X-rays, both standard one and synchrotron type techniques, and some techniques that we do not possess here in South Africa and in the whole African continent. So, Prof. Najibou, to you.
Thank you, Malik. Thank you for the introduction. I'm going to speak about calcium carbonate today. And I don't know, maybe some of you have never heard about calcium carbonate. So who has never heard about calcium carbonate? All of you have heard already about calcium carbonate. Oh, my talk is finished then. I don't need to speak about calcium carbonate. Like all of you know about calcium carbonate. Well, but maybe you don't know exactly the subtleties about calcium carbonate, and so I'm going to move to the first slide, maybe. Does not work anymore. Yes. Which one? Okay. This one. What? That's good. You were working nicely. Yeah, I was checking now. Is there anything stuck?
Can you use your mouse?
Maybe your mouse. Click on the.
Ah, all right. Yes. Can you remove the one of the top?
Is recording now.
I'm telling you, space about the one that's like
Oh.
All right, pretty good. So yeah, if you think about calcium carbonate, the first thing that you can find is that it is something that is going to be deposited over time. So if you are in a place where there is a lot of calcium ions in the water, you will see clearly that after a certain amount of time, you will observe some deposit on your tap. And it's even more severe in the pipes, where it can provide some clogging in the pipes. But you also find calcium carbonate in natural caves as stalactites. And in this case, it takes a very, very long time to make stalactites, maybe several years just to grow a few millimeters of calcium carbonate. And another place where you can find calcium carbonate in Greece. So if you are aware of what's going on in geography in the northern part of France, you have the Etretat cliffs, which are made of calcium carbonate also, and you can see that they are made of very nice layers, and I will explain why it is the case later on. But you can also find calcium carbonate in quarries, especially marble quarries, and one of the most famous ones is Carrare in Italy. It's a white, very nice white marble, And you can also find this in hot springs. This is just a few examples where you can really encounter calcium carbonate in the daily life. But here in South Africa, you have many places where you can see calcium carbonate from shells. And typically, the abalone is a shell that you can find here in South Africa. The nautilus, coral reefs, they are made of calcium carbonate. Pearls, for the ladies, if you like nice pearls necklace. Well, this is just calcium carbonate. And one of my favorite is the coccolithophore. They're very small pieces, a few microns, algae making calcium carbonate shells. And oysters, if you like oysters, well, the shell is made of calcium carbonate. One key point in calcium carbonate studies is the biomineralization. And typically, if you look at what's going on in a shell like this one, you will find out that the calcium carbonate is made of a very fancy architecture where you have in the calcium carbonate some organic materials which are guided the growth of the calcium carbonate, and in this case, it's aragonite. Well, you can see in this recent PhD sequence of the Sorbonne that the structure of nacre is extremely fancy. You can see that it's really something which is made of very nice organic layers. And then, well, you have a sequence of tablets which are formed on top of the organic material. Another place where you can find calcium carbonate every day, if you eat the eggs in the morning, well, the shell of the egg is made of calcium carbonate, and the snail shell is also made of calcium carbonate. And in architecture, just to give you a few examples where you can find calcium carbonate, you see here for the Indian people in this room, the Taj Mahal is made of calcium carbonate. And if you go to Greece, the Parthenon temple is also made of calcium carbonate. And in this case, it's a metamorphic calcium carbonate, meaning that it has been made at high pressure and high temperature, and it's a very strong calcium carbonate. So why do we want to study calcium carbonate nowadays? When I started this story of looking at calcium carbonate, I thought, well, there is no point of studying calcium carbonate. Like if you want to study silicon, for instance, who is studying silicon at the moment? Not so many people, because everything is known. In the case of calcium carbonate, why do we want to study this? Mainly because it's one of the compounds which is used extensively in the industry. So typically, if you look at a piece of paper in front of you, you have about 30% of calcium carbonate in a piece of paper, because this is something which is making the piece of paper white. The whiteness is really related to the calcium carbonate, and it's also increasing the strength of the paper. You can find this in rubbers. In the chemical industry, every thing that you can find in paints, well, usually it's made of calcium carbonate. And in medical, in drugs, every time you take a tablet, this is also calcium carbonate. Part of it is calcium carbonate, in which you have put some medical drugs. And you see here, well, a report here on how much calcium carbonate is going to be used in different parts of industries. And this is why calcium carbonate is so much studied. How can we make calcium carbonate? Now, in the lab, it's very simple. You take calcium ions, so for instance, calcium chloride. You take some carbonate ions, sodium carbonate, you mix the two, and then you will see immediately that you will get a precipitate. So I need to start the movie here. If you don't know when you can start. it is a reaction. So it is a solution, and you observe a precipitation of the calcium carbonate. And you can modify what's going on in the beaker here by tuning the parameter. You can change the concentration of the solution, you can change the temperature, and you can change the steering speed, and then you need to filtrate this solution in order to get the calcium carbonate. And basically what you are going to observe, depending on those conditions, are 3 types of calcium carbonate, because calcium carbonate is made of 3 types of polymers: calcite at the top, aragonite, which is the middle one, and vaterite, which is the last one. And you can see that these different types of calcium carbonate are very different in terms of morphology. So the calcite is made of rhomboidal materials, the aragonite is made of rocks, and vaterite is a porous structure made of spherical particles. And what you can see also is that if you try to understand what's going on from a thermodynamical point of view, the stability of those materials is going higher in this direction, meaning that calcite is more stable than aragonite, than vaterite, and than the amorphous calcium carbonate. But from a kinetics point of view, the easiest way to form calcium carbonate is to form the amorphous calcium carbonate. Okay, and then, well, you can form vaterite, aragonite, and calcite. And actually, the amorphous calcium carbonate and the vaterite are metastable phases, and so it means that they can easily transform either in aragonite or calcite. How does it work also? Well, I have shown you that you have different types of polymorphs. So if you want to know what type of polymorph you have, you can make scanning electron microscopy. It gives you an idea because you have the shape. But you can do also X-ray diffraction, and X-ray diffraction gives you, when you do the powder X-ray diffraction, you get a pattern in which, if you have a mixture of the 3 components, you can see that they are very different. The bright peaks are in very different locations. So typically in green, you have the vaterite, in red, the aragonite, and in blue, the calcite. And if you know how to analyze those data sets, you can find how much of each polymorph is composed in the powder. So how does the precipitation occur? In order to do a precipitation reaction like this, you need to satisfy one condition. You need actually to look at the solubility product of all those materials. And actually, you can only precipitate calcium carbonate provided that you're in a supersaturation state. What does it mean? It means that you need to have this quantity omega, which is the supersaturation value, which is going to be greater than 1. And how does it work? Well, for instance, if I am working with 8 millimolar solutions, so I have a concentration of calcium, which is 8 millimolar, concentration of carbonate, 8 millimolar. I can do the product of the two, and I can look on this graph what is the KSP of the amorphous value. So at 20 degrees, the KSP here is of the order of something like 500, maybe 600. So I can calculate the values of omega, and you can see that, well, in this case, at 8 millimolar, I am well above the saturation, the supersaturation of calcium carbonate. So this is going to precipitate. Nonetheless, if this quantity, so if calcium ions are in very low concentration or carbonate very low concentration, you might end up with something which is less than 1. Okay, and in this case, there is no way that you can precipitate calcium carbonate. Okay? So this is the basic idea behind this. And of course, I mean, this is what you need to do if you want to do this type of reaction. One thing that we have been learning about working on those materials is that we can delay the precipitation. You could see that in the previous movie that immediately when you mix, you can see that after maybe 1 second, you immediately get a precipitation. Nonetheless, if you use, for instance, polystyrene sulfonate, which is these molecules, polystyrene sulfonate likes very much to bind to calcium. And in this case, you can see that here you have sulfur moieties here. And this sulfur, if you can modify the ratio between sulfur and calcium. And at 0 ratio sulfur over calcium, you see that immediately you precipitate the calcium carbonate. So if you don't put PSS into a solution, there is no way that you can delay the precipitation. But you can see that if now you put a sulfur over calcium ratio atomic values of 4.7, you see that the precipitation begins to occur after 60 seconds. So it takes a long time. Maybe you can go even more than this, as you will see later. And so one of the key questions is that if you really want to study the precipitation of calcium carbonate, you need to find the right technique for that. And that's not so easy. So we want to study this, and basically we want to study the kinetics of reaction of calcium carbonate. And I am going to show you how we can do that now. So how we can study the precipitation, you can take the camera and do exactly what I did before, but that's not going to give you much information. Okay, you will see, well, some turbidity in the solution, but you will not be able to understand what's going on deeply inside the solution. So for this, what we do, we go to the synchrotron, and one of the good synchrotrons that you can find in the world is ESRF in Grenoble in France. This is one of the best synchrotrons in the world. And how does it work? Well, you see, you have a ring like this. So the ring is this. And actually what you do, you use an electron gun with a linear accelerator, and you accelerate electrons. Those electrons, you put them in a cyclotron. I think here in Itemba Labs, you are having a cyclotron now. So you put this into a cyclotron, you accelerate them, and when the energy is high enough, you store them into the ring. And next, every time, so you store them, but these electrons are going to have the velocity of light, so it's ultra relativistic particles. And when they go inside, well, this ring, they go either in straight lines, so they are not accelerated at all, they have the speed of light, but every time they go into a magnet, they are accelerated in the magnet, and they create a very intense X-ray beam every time they go through a magnet. And this is this beam that we are going to use at the synchrotron. Compared to what you can get in a lab, the brilliance of the synchrotron is, well, orders of magnitude, 10 orders of magnitude bigger than what you can get in the lab. So it means that you have very intense beam, and you can do experiments at a very high speed. And what I'm going to show you is the kinetics of reaction made by in situ SACS. From SACS means small angle X-ray scattering studies. So what is SACS? It's an experiment during which you are going to use a sample. It could be particles which are forming in a liquid, or it can be a powder. You shine X-ray on this sample, and you measure at a long distance from the sample the small angle X-ray scattering data sets using a 2D detector. So you go at very long distances. So it means that when you are doing those experiments, theta is very small. So since theta is small, It means that you are working at small angle, that's the definition. And it's also something which allows you to probe materials having a size which is inversely proportional to Q. So Q is 4 pi sine theta over lambda. So if theta is very small, Q is going to be small. And as Q is related to the inverse of the size, the smaller the Q, the bigger the size of the sample. So if you are looking at very small Q, you can look at big materials. So it would be the same as if you go into a game park, in the far end, you see the elephant. Okay? So you are at small Q. So you see the entire elephant. But if you go much closer, the angle becomes much bigger. And then what do you see if you are very close to the elephant? You cannot distinguish the total form, the total shape of the elephant, but you will see only the skin of the elephant. Okay, that's the same with small angle X-ray scattering data. And so what we do usually when we do small angle X-ray scattering, we have a 2D detector, we measure a scattering pattern, and then we do radial averaging. And so for instance, in this pattern, you see that you can get this, and typically you can transform the pixels. Well, if you are the y distance in pixels here, divided by the distance from the sample to detector, you can calculate theta, and then you can calculate Q, and you can convert the data set into intensity versus Q. Okay, so at IT2 at the ESRF, this is one of the very, very best SAX beamline in the world, mainly because you see, well, we have a tunnel like this. In this tunnel, you have a very high vacuum, and you can have a detector which can move from a position which is typically, where is it? The sample is here, from about a few meters to about 30 meters. This location is 65, here is 95 meters. So you can move 30 meters away from the sample. And you can imagine, I mean, if you could try to put this setup here in this room, it will not be possible. This room is less than 30 meters long. And so this tunnel here is 30 meters long, very, very long setup, very impressive. Okay. And if you do experiments, for instance, on polystyrene latex particles, this is the 2D detector. This is the radial averaging of the data set. And you can see that, well, you see beautiful fringes. Okay. And those fringes are typical of particles having a radius, an average radius of about 1 micrometer. So 2 micrometers in diameter. So you can, well, evidence particles having a total diameter of 2 micrometers at this beamline. Very difficult to be able to do that in other setups, SAX setups. Okay. So what have we been working on? We have been using what we call the flow cell. And what is the flow cell? This is what you can see on this screen here. So you have a beaker, and in this beaker, you are going to pour the two solutions that you want to study. So typically, sodium carbonate and calcium chloride. So you mix this, and of course, as soon as you mix the two solutions, the precipitation reaction starts. But at the same time, you have a pump, and you pump through this setup, you pump the solution, which goes into a capillary, and you shine the beam inside the capillary. So the reaction is occurring, but during the reaction, part of this solution goes through the capillary, and then you can measure, as a function of time, what's going on inside the capillary. So this way, you can look at the way the precipitation is occurring. I need to go a little bit into the details of the calculation. So if you just put a particle in a solvent, you can work this out. You will get the Fourier transform of the density of the particles minus the one of the solvent. That's what you are going to measure. And if you try to calculate this, you can find out that you will end up with an amplitude which is given by this relationship, in which the Q dependence is given by this equation. So that's not very difficult to calculate. You can put this into a computing program and you can calculate this. And now if you put many particles but in a diluted regime, so it means that they are not really interacting between each other, well, the scattering is going to be like this, and you are going just to add, well, the intensity of one particle is multiplied by the number of particles divided by the volume of the solution. So you will end up with something which is going to be proportional to the concentration. Okay. And just to show you what's going on here, well, this is what you can get with a particle which is 150 nanometer in radius. So you get this curve, beautiful, nice curve. And now, if you add some polydispersity, meaning that when all the particles are not having the same diameter, well, you can see that instead of having very pronounced dip here inside the curve, you will get, well, the oscillations which are going to be damped. So by doing measurements like this, you can first of all get, well, the radius of the particles, and second, the polydispersity of the particles. Okay. And so if you try to calculate what's going on in this case, you can find out that, well, if you are in a regime where QR is very big compared to 1, well, you will end up with an asymptotic behavior for the scattering, and typically the asymptotic behavior is going to be 1 over q to the fourth. And so it means that this curve is going to decay as 1 over q to the fourth, which you can see here. You see the decay here is very steep. Here you're at 1, but here you're at 10 to the minus 5. And it means that as soon as q is increasing a little bit, well, the intensity is going to decrease very fast. Okay? So this is what is known as the Broad law. And well, you can find out that also that's a bit interesting to comment here. You can see that if you mix 2 types of particles, one which is 150 nanometer in diameter, and one or particles which are 15 nanometer in diameter, what's going to happen? Well, for the 15 nanometer, the scattering curve is like this. For the 150 nanometer, it's a blue one. So you can see immediately that at very small q, the big particles are going to dominate the scattering. But at very larger q, the scattering is going to be dominated by the small particles. Okay, so that's also very interesting, because in this case you can understand that, well, if you get something very intense at small q, it can come from small particles. But everything you see at very small q is usually coming from big particles. And if you have a mixture of particles, well, the big particles are going to dominate the scattering at the end. Another thing that you need to understand is that instead of plotting I as a function of q, you plot I q times q squared as a function of q, you will end up with a maximum. So why is that? Mainly because if you multiply this curve by q, q is small, well, small q times something which is constant, you see that it's going to go up as a function of q, okay? And then when q becomes big, well, it's going to decay again, but it will go through maximum. So this is what we see here. Same story, the 150 nanometer particles, you can see that if you plot the scattering curve as a function of q, but I q times q squared, it goes to a maximum. And the maximum value here is related to the radius of the particle. So it's a very smart way of measuring directly the radius of the particle. And you will get also something very interesting. The total integrated intensity below this curve is a constant. Okay? So what are we going to observe when we do our experiment? Something like this. So if you have understood what I've told you before, this is as a function of the time of reaction. So at the beginning, well, you see a slope like this, but after a certain time, you begin to see a saturation of the curve and some oscillations which are faint. So coming back to what I told you, this is telling you that you have polydispersed particles, okay? And those polydispersed particles, well, they are growing in terms of number because the intensity is growing. And if you look at the evolution of the radius, so the fringes, they get closer to each other. So it means that the particles are getting bigger in the solution, okay? And if you plot this in terms of Kratky plots, you can see that, well, there is an evolution of the maximum position of the curve, meaning that I told you this maximum is inversely related to the radius of the particles. So if this maximum is going like this, it means that the particles are growing. Okay? And actually, now we can plot the Porrod invariant, and this Porrod invariant is evolving like this. So what does it tell you? It tells you that the Porrod invariant is growing, and what is the Porrod invariant? It's the concentration of the particles times the difference in densities of the particles minus the solvent times the volume of the particle. So what you see here is that, well, the growth of those particles is, well, actually arriving at about 170 seconds and into a burst. Means that very suddenly the particles are forming, but before there were a few nuclei inside the solution, and those nuclei, they were quite small. If you look at the evolution of the Porrod, you can say that well, the growth is starting about 170 seconds. It goes very fast, and then it's finished. So, okay. And well, you can try to understand what's going on if you modify the concentration of the solution. So at 9 millimolar, you see that. 7 millimolar, you see that. For 4.5 millimolar, you see that. What is the conclusion? What would be the conclusion? Looking at those drawings.
Higher the concentration, larger particle.
So higher the concentration, that's this one. So you say, in this case, I have larger particles. Wrong.
Wrong.
Wrong statement. Wrong statement, because I told you the maximum of the Kratky plot is inversely proportional to the radius of the particle. So here you see maximum is here. So the radius is 2 pi over this quantity, so you can calculate it. But if those are the same ordinates, okay? So if the maximum is shifting towards smaller q, it means that in this case you have bigger particles than in this case. Okay? And this is also the case here. Okay? So just by looking at the Kratky plot, you get an information about the radius of the particles. And in this case, you find out that, well, the smaller the concentration, the bigger the particles. So you could ask yourself, why it is the case. I will come to this later on. And you can see the evolution of the Klampke plot as well, of the poroid invariant. In this case, well, for the 9 millimolar, 7.5 and 4.5 millimolar. So this is what we have found. And if you look at the evolution of the radius as a function of time, you can see that in the case of the 9 millimolar, you end up with a radius of 200 nanometers. And you start at something which is of the order of 25 nanometer. And in this region, you have a mixture of two types of radii. And it means that you have some pre-cluster forming, and those pre-clusters, they are transforming into big particles after a while. Okay? So typically when you see that, you see at the beginning they are very small. In this case, you have small particles and big particles which are starting to form, and very quickly, well, you form the clusters of calcium carbonate. Okay. And in this case, we were not able to look at the starting of the experiments, because if you do an experiment, you mix the solution, you have to close the door of the hatch where you do the experiment, and to start the experiment from the computer. It takes about 60 seconds. So we could not be able to do experiments at the time, well, below 60 seconds in this case. Okay. So we have bigger particles when the concentration is small. Why that? Mainly because we were working at a constant concentration of PSS. And if you work at constant concentration of PSS, well, it means that, well, if you are less concentrated solutions, you have more PSS per particles. Okay? And the PSS is governing the shape of the particle in this case. So you can do scanning electron microscopy, and this is indeed confirming what we have been looking at. And this is the conclusion of this experiment. I hope that I have convinced you that in the case of small molecular X-ray scattering, you can look at the formation of particles in situ, in this case precipitating, or if you look at other materials, like I know a lot of you are working in silver formation using plants, you can look at the evolution of the silver particles as a function of time as well, in solution. And if you do the analysis correctly, you can get a lot of information that I have no time to discuss here today because it's not yet finished. So these are the people who have been working with me on this type of experiment, typically people at IT2 and people from NTNU in Norway, with whom I am collaborating. And so now I will move to another story, which is coherent diffraction imaging. And in this case, what we want to do is to perform small angle X-ray scattering experiments, but with coherent X-rays. So we use X-rays which are coherent, like for a laser beam, and we shine those X-rays onto the surface of a material, which is deposited onto a membrane, and we measure the scattering pattern at a very long distance from the sample. What do we get in this case? Well, we get a 2D pattern, and this pattern contains what we call the speckle. So you can see that there are small grains in this scattering pattern, and the speckle is related to the fact that the system is not homogeneous. It's not a full sphere or full particle, but there are some holes inside, and this is creating the speckle. And how do we analyze this? Well, I forgot to say that we do that as a function of the rotation of the membrane. So it means that at each angle that we are going to rotate, we will get a 2D pattern like this. And this is the basics of what we call the tomography. So if you have some problems medical problems. You can go at the hospital, and at the hospital, well, they can make some analysis, for instance, of your brain, and they make a 3D image of your brain. So this is what we call tomography. So what they do in this case, they don't rotate your head, but they rotate the source. Okay? And at each position of the source, they take an image. And once you have done that, you recombine all the images and you get a 3D picture of your head in this case. And in this case, we have fixed X-rays, but we rotate the sample. And at each rotation, we take a 2D pattern and we try to analyze this. So how do we do that? We take from the picture the square root of the intensity. We put an initial guess phase and we invert this. So when you invert that, you get the electron density profile. And well, of course, if you don't know the phase, you do that, you will get the wrong electron density profile because the phase is not correct. And what you do, you put some constraint. So it means that the electron density of the material needs to be positive. So everything which is negative, you kill it. You put something which is either 0 or positive. And in addition, you need also to say that outside from the sample, so typically in this case a few microns, the electron density should be 0. And then you calculate again the Fourier transform of this new electron density which has been constrained, and you compare it to this. And you do this iteratively, and after a while, you can get the right phase. So it's called the phase retrieval algorithm, which is something which has been of course, provided by the people at the beamline, and I didn't go through the calculation by myself, but use the program, and in the end, you can get a full description of the image of the sample. So just to show you a few things about this type of technique, if you take a cube like this, you project the cube on a 2D plane. You will get something like this. If you Fourier transform this guy, well, you will get this. So you will get something having the same symmetry as the cube. So you see, you will get fringes like this. And if you take this Fourier transform and you know the phase of the phase in this case, by inverting the amplitude and the phase, you will get back the image. You do the same, but you don't know what is the phase. So you take that, you will get the amplitude, but you don't know what is the phase. You try to invert it, you will never get back to the image. Okay? So it means that if you really want to get back the image, you need to know the phase. This is why we need to use the phase retrieval algorithm. And just to show you another thing, if you take a full sphere like this, you Fourier transform it, you get this scattering pattern, having the same symmetry as the object as well. Okay? If you take now a sphere, but you put a hole inside, like this, you get something in projection. And if you do the Fourier transform, you can see that you get the rings, but at the same time, you get some kind of modulation in the ring. That's what we call the speckle pattern. Okay? And the more holes you are going to put inside, the more speckle you are going to see. Okay? So it means that typically when you release this type of measurements, you will use a membrane, very small membrane, 100 nanometers thick. You will deposit your sample on it. You will put the sample onto the stage of the beamline, and you will start making experiments at a long distance from the samples, which is here, and the detector is over here. Okay. So what I want to show you now is what we have been doing on precipitated calcium carbonate particles by coherent diffraction imaging. And well, if you do an experiment like this one without polystyrene sulfonate, usually what you will get is vaterite And if you leave this as a function of time, the vaterite is going to transform into calcite. So vaterite, I told you, they are spherical in shape, porous in terms of structure, but the calcite is very dense. Okay, so there is what we call here a metastable particle, which in solution is going to recrystallize into calcite like this. Okay, and if you do the scattering, the electron microscopy on the same sample, that's what you get. So you see, this is coherent diffraction imaging. This is what you do in electron microscopy. Of course, I mean, there is pollution because you have to deposit some gold on top of it to do the electron microscopy, but you see, it's exactly the same. So it tells you that the reconstruction that you can do with coherent diffraction imaging is correct. Okay. So what we did the same, but now in presence of PSS. So after 1 minute, this is the electron microscopy in transmission. You see, you get something black, completely black on the particle. What does it mean? It means that the particle is full because it's completely absorbing, and that's what you get. After 30 minutes in the solution, so these particles, they were kept aged at 75 degrees in the solution, and after 1 minute, you get this. After 30 minutes, you get this, and if you do coherent diffraction imaging on the same particles, you get that. Okay. What do you see? Huh? That's challenging.
Yeah.
So let us compare two things which are comparable, those two ones. You see, well, it's fully black here, but in this case, it's not really fully black. And what you can see is that there is a white part. Okay. And here in X-rays, it's white here. Now it's black here and white on the crest. So it means that you have formed here something which is well, no more homogeneous in terms of density. And so if you really want to know what's going on, well, you try to understand the 3D image, coherent diffraction imaging. And here is the top view of the particles, and here it's a view on the side. And you can see that the particles is slightly shrunk in one direction, but well, you don't know what's going on inside so far. So you continue your analysis and you find out what's going on inside the particles. And so this is after 2 hours of reaction that the particle from the top, from the side, it cuts through the particle. So you see that now you have a core and a shell, and in between nothing. And here, that's just a cut, just one part of the particles, but here it's half of the particles. So you can see the interior of the particles, you can see the crust, and you can see how it's working after 2 hours of reaction. Now, if you take 8 hours of reaction, you begin to see something even more different. So typically, well, these particles has been transformed into particles with much bigger particles in the crust and with less particles inside the core. Okay. And if you go after 24 hours of reaction, you get something like this, nothing left in the core, just the crust with big calcium carbonate particles, which are made of vaterite particles. And very interesting as well, you can see that if you look at the poles of the particles, there is not so many crystals. Okay. So maybe you can just start the movie. Yeah, so you see, this is what you can find out with the 3D coherent imaging, you can see that you can observe inside the particles and you can observe in 3D how the particles is doing. So it's a very beautiful way of analyzing data set like this. Okay. And so, well, we were trying to understand what was going on. And typically, what we found out is that all those little crystals which are formed at the surface, which are lateral crystals, they tend to align along the meridian of the particles. Why is that? Mainly because, well, those particles, well, they are polar. And because they are polar, well, the dipole moments, they try to align parallel to each other. But there is a frustration at the top, because if you put many dipoles at the top, they don't want to have their dipolar moments parallel to each other. So it means that at the pole of the particles, you cannot form crystals. So this is why the polar structure here at the top is depleted in terms of crystals. You don't see many crystals here, but you see mainly the crystals along the equation. And just to show you another way of understanding what was going on, we have been working on fluortomography as well. So what is this technique? It's on another beam. We do fluorescence of the elements, and we do 3D images with a given particle at different energies, and we can locate, for instance, the calcium and the sulfur inside the particle. So in this case, you have an image of a particle with just the calcium. So the other one here, a quarter of the particles is the calcium, and here this is the sulfur. So you can see that the sulfur is located all over the particle. So it means that the PSS goes completely inside the particles, and so that was quite interesting because it was very difficult to know where the PSS was going during the classification. And well, you could say, okay, we have learned perfectly well what was going on. We wait a long time and we get a core shell particles with hollow core after a long period of time. But that's not true. Because if you modify the concentration of the particles, instead of working at 8 millimolar, you work at 30 millimolar, then you find out that the particles never get completely hollow. You get something which is very porous. And so that was also explained in terms of the ratio of sulfur to calcium. Don't want to go too much into the details, just to show you that this story that was at the beginning quite simple was not so simple. So if you modify the concentration of the solution, this is not necessarily true to make all the particles. And that was an explanation for the dipolar moments. So you can see that depending on what you are doing, well, you have the dipolar moments which are along the meridians. So in this case, you can see that, well, the dipole moments, they go all in all directions, and they cannot let crystals to be formed at the pole of the crystals. Well, conclusion, well, we were able to do that and to show that we were having core shell particles. And the story is a bit complex if you look at what's going on in the function of concentration. And just to finalize what I was showing you, just calcium carbonate can be produced also by algae. And so maybe you can start this movie. So algae, they have membranes like this. And you can see that in this movie, well, there is a chemical reaction occurring inside the membrane of the algae. And this chemical reaction is producing some, well, systems that we call coccolith inside. And those coccolith, all of a sudden, they are expelled from the membrane and they are covering the surface of the membrane. Okay. So this is what those algae are able to do. And one of the key questions is, what is this? Well, this is this, okay? And this is this, and actually, what you see here is what we call the cocosphere. And what is a cocosphere? This is a calcium carbonate material. Those coccoliths here, they are made of pure calcite. Okay? So those are calcites. And if you try to do this for yourself in the lab, try to make something like this. Well, if you succeed, just come to see me because I would like to know what is the recipe, because it's absolutely impossible for any chemist to do that. You could take the best chemist in the world, Nobel Prize in chemistry, ask him to make something like this, won't be able to do it. Okay? Because actually, this type of calcium carbonate is made by biomineralization inside the membrane of these algae. And those algae, they know how to do it. How they do it, we don't know, but they know how to do it, and they know to reproduce this as a function of time all time long. Because those type of materials, they exist since about 100 million years ago. So they know how to do it. So they are very smart compared to the Nobel Prize in chemistry. But there is a but. They know to do only this. So if you ask the algae to do titanium dioxide or vanadium dioxide, they could not do it. They can only do calcium carbonate in this type. So that's a mystery how they do that, but they are able to do that. And what happens to this coccolithophore? In the oceans, they are eaten by shrimps. So the shrimps, they digest this, not very fancy, it's not a fabulous technique, but nonetheless, this is what you get here, because the digestion of this is made of calcium carbonate. And during the Cretaceous, 100 million years ago, the oceans were far above those cliffs. And then the level of the ocean was decreasing, not like what is happening at the moment. So the level of the ocean was decreasing, and then appeared all those nice stacking layers made of coccolithophore. So if you go to Etretat, you pick up a piece of this cliff, it's full of coccolithophore. Okay. So very interesting. And so now if you click here, you see with the quantum diffraction imaging, you can see completely what's going on. And if you click on the other one, the very good thing about having a 3D image is that you can segment it. And you can segment and you can isolate part of the cocosphere and isolate coccolith. Why do we want to look at coccolith? Do you have any idea about that?
Drug delivery?
For?
Drug delivery?
No, not at all. Not for drug delivery. Because I mean, this is what you can find in the oceans. So it could be possible indeed to put maybe drugs inside, but this was not the reason. In this case, this is related to CO2. So CO2, how do you form a cocosphere? You form a cocosphere, you need calcium, and you need carbonate. How do you get the carbonate in the oceans? How can you get carbonate in the oceans? Carbonate ions.
It is no CO2 and
You dissolve CO2. So CO2, which is made by anthroposophic production, is produced in huge quantity and it goes into the oceans. So when it goes into the oceans, what's happening? CO2 is dissolving, and what is going on when CO2 is dissolved in water? CO2 plus H2O is forming Carbonate not yet, but it's forming H2CO3. H2CO3 is what? Carbonic acid. So it's an acid. So it's an acid, and it means that if you put CO2 in the oceans, you are going to decrease the pH of the ocean. And if you put calcium carbonate with an acid, what's going to happen? If you want to wipe out the calcium carbonate in your tap, what do you do? What do you use in your kitchen? Well, so I can see that many of you don't go in the kitchen.
They're not clean.
Huh?
They're not clean.
They don't clean.
No. Most of them they have here.
Ah, so they don't clean or they never go to the kitchen. But if you have calcium carbonate deposit into your kitchen, how do you remove it? You use acid and you use what type of acid that you will find in your kitchen?
Vinegar.
Vinegar. So you put vinegar on this, and this is going to clean completely your calcium carbonate. So it means that calcium carbonate will dissolve in presence of acid. So if you put this small dot in presence in acidic conditions, it's going to disappear. That will be a pity because, of course, having algae making calcium carbonate and pumping the CO2, which is what provided by the human beings, this is a very smart way of avoiding us to be to not to be able to breathe anymore. Okay. So if the CO2 is increasing too much, you know that this is the case at the moment, but still okay because of the ocean. Well, if those guys are no more existing, I can tell you, we are going to disappear very soon. So the key point is we want to address, in this case, how much is the mass of a coccolith. So how do we do that? We do coherent diffraction imaging. We isolate coccolith. We know that coccolith are made of calcite. We know the density of calcite. We know the volume of a coccolith from the experiment, and we can know the mass. You know what is the mass of a coccolith approximately? 1 microgram. Any other suggestion? 1 microgram, you are not at all correct. The mass of a coccolith is of the order of the picogram, because the microgram with the parts balance, you could be able to measure it. But picogram, there is no way that you can do that. If you can start the maybe. So you see now we are going to see what's going on inside the cocosphere, and you can observe the formation of the coccolith. And this is the only way that you can do it using coherent diffraction imaging. There is no other way of doing that. Okay. And so in this case, well, you should start this one, or maybe I have to do it. You see, this is the coccolith, and look at the magnificence of this guy, with very nice grid here of the order of a few nanometers, and we can completely isolate those coccoliths and measure them. And in this case, we were able to show that with different species, the mass is depending on the perimeter of the grid. So if you know the perimeter of the grid, you will know what will be the mass, mainly because those little elements which are making the coccolith, they all have the same width. Why is that? We don't know. Again, I mean, ask the algae if you can, but there is no answer. So why in a coccolith each element has exactly the same width? And so, just to finish this, well, I hope I have convinced you that coherent diffraction imaging is really a very good technique to image small materials. There is a limit because the materials need to be less than 10 micrometer in size, because well, the coherent beam is coherent over 10 by 10 micrometer. And typically, well, you can image and you can extract a lot of information. You can start maybe this movie also. That's the last one that I've been measuring. So cocolith made of calcium platelets again. And you can see that that's the shape of a trumpet. So what those algae are making sometimes, well, cocolith, which are the shape of an Emilian saying. Why they make trumpets? And if you look at, well, the wealth of cocoliths that you can find in the oceans, there are many, many of them which are different. And what is the purpose of those cocoliths? That's a good question. Sometimes people they say that they protect the membrane. Other people say that since they can expel the cocolith from the membrane, they could well, play a role on the like a submarine. So if you put more cocolith, the cell is going to go down. If you expel some cocolith, well, the algae is going to go up. So if the algae likes to have sunlight, it will go up in the vicinity of the surface. But if the cell wants to get nutrients, it will go down. Okay? And in this case, the trumpet, what could be the use of the trumpet? Well, we have tried to look at the shape of this trumpet and to find a beam of light, just a normal light, visible light. And what we have been able to see is that the trumpet is concentrating the light onto the cell. So basically, this trumpet has a function which could be just collecting the light onto the membrane. So you see, well, it is a very interesting system to be studied. And with this, I will stop here. And I thank you for your attention. And those people are the people who have been working with me on the calcium carbonate story. Thank you.
Thank you so much, Prof. Management, for this inspiring talk indeed. So we have time for questions. Please.
Question. Hi, Prof.
Hi.